Okay, Assalamualaikum warahmatullahi wabarakatuh. Our next topic is chapter 8, which is goodness of fits. Okay, the sample data goodness of fit is a sample data of observed frequency count arranged in a single row. So we call it as a one-way frequency. Okay, table. So we will test the claim that the observation frequency count agree with some claim distribution. So in other words, there is a good fit of the observed data with the claim distribution. Okay, what is a goodness of fit? A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits some claim distribution. Okay, so goodness of fit of test notation is O represent the observed frequency. Okay, E represent the expected frequency. Okay, K represent the number of different category and represent the total number of trials. Okay, the requirement you have to have a data have been randomly selected. For each category, the expected frequency at least 5. Sorry, so there is no requirement of observed frequency in each category. So this is the formula of test statistical goodness fit of test. So this is x square test, which is chi square. So what is the formula? Is the formula x square equal to summation of O minus sum E square, the summation, total summation divided by E. Okay. So for example, we can find usage a table K minus 1 degree freedoms where K equal to number of category. Goodness fit of hypothesis test always right tails. Okay, another one you need to know is about P values. P values are typical provided by computer software or range of P values that can be found from the table given after this. Okay, so if all expected frequency are equal, so we use E equal N divided by K. Okay, the sum of all observed frequency divided by number of category. Okay, if expected frequency are not equal, we use E equal to NP, where is your N is multiplying the sum of observations frequency by probability of the category. So if you have probability, you use this one. If not, you use the N divided by K. So the close agreement between the observed and expected value will lead to small value of x square and large value of P. A large disagreement between the observed and expected value will lead to the large value of x square and small value of P. And the significant large value of x square will cause a rejection of the null hypothesis of no difference between the observed and expected. So you can understand, you can use this term. If P is low, null must go. So means if P is small, reject the null hypothesis that this distribution is a claim. Okay, you can see here. So if a relationship among the x square test statistics, P value and goodness fits. So when you compare the observation of O value of the corresponding expect, you have two conditions. One condition, or S and ES are close. So which is x square small value larger than P. So if your x square is inside of this region, so it's failed to reject. So good fit distributions accepted. Okay. If your x square in this area, so it will be reject HO if the P is low and the null is must go. Okay, if P is low, so we will reject. So not a good fit test. So inside of this area will be accepted. Okay, outside of this one will be rejected. So for example, we have a set of A appendix including weights of 40 random selected adult males and 40 random selected adult females. So we have 40 males, 40 females. Okay, those weight were obtained as a part of National Health Examination Survey. So when obtained weight of subject, it's extremely important to actually weight individual instead of asking the reports. So by analyzing the last digit of weight, researcher can verify the weight were obtained through actual measurement instead of being reported. So when people report weight, they typically round for the whole number. So the report weight tend to have at least last of 0. So in contrast, if people are actually weight, so they have a scales, where is nearest of 0.1 pound. So the end of the scale will be number. So if you can see from this, for example, the weight of 201 5 pound as a number of 5 at the end. So we want to the data will be more realistic compared to the without the point here. Okay, so then the claim that the sample is from population of weight in which the last digit do not occur with the same frequency. Based on the result, what can we obtain is, for example, this is your the data. So the last digit 0 is 7, the last digit 5, 1 is 14, 2 is 6, last digit 3 is 10, and the last digit 9 is 8. So this is the frequency of the last digit. So in order to solve this one, so we require to randomly select the subject frequency count, which is expected age is bigger than 5. So we have age is bigger than 5. Okay, 8 is bigger than 5. Okay, so step number 1, at least one probability of P node P1 is different from the others. Step 2, at least one probability are the same. Okay, at least one. And 3 is null hypothesis contain equality. So which is H node is equal, H1 at least one is difference. So in this case, there is no significant specifics, so we use this alpha is 0.05, and the testing whether uniform distribution goodness is x square. We use x square. Okay, so see the next slide, which is x square test statistic. X square equal to 11.25 using alpha is 0.05. So where is your k minus 1 equal 9, degree of freedom, and critical value is. So for example, you have O, this is your table observation. Okay, so total of this one you get 80. So this is your O data. So your expected is 8. Okay, 8 is n divided by k. We use n divided by k. So your n, total n is 80 divided by k is 10. 9, 0, 10. So you get 8 for examples. So O divided by E, for each one you get negative 1, 6 and the rest. O divided by E square is 1, 36 and the rest. Then you calculate O divided by E divided, you get 0.124.5 and the rest. So the total of this one you will get 11 point, total of this one, summation of this one, you get 11.25. So this is for your x square. Okay, so as been mentioned previously, your x square of critical value is 16.91. So when you put it this bell curve, you know that 16.91 will be in this range. But your data x square is 11.25. So you see 11.25 stated inside of this green color. Okay, it's failed to reject. So because of the test doesn't fall in the critical region, there is no sufficient evidence to reject the null hypothesis. So we accept because it's under this category. Okay, so there is no sufficient evidence to support the claim that the last digit do not occur with the same relative. So the goodness fit test suggests that the last digit provided reasonable good fit with the claim distribution equal likely frequency. Instead of asking the subject how much they weight, it appears their weights are actually measured as well as should have been found. Okay, we go for another examples here. Okay, for chi-square test goodness, what we will basically learn after previously is state the appropriate hypothesis and compute expected count of chi-square test for the goodness fitness, calculate the chi-square test, degree of freedom, and p-value as chi-square test, and perform chi-square test for the goodness of fit, and conduct follow-up analysis when the result of chi-square test are statistically significant. Okay, sometimes we want to examine distribution of single category. The chi-square test allow us to determine whether the hypothesis is distribution invalid. So we can decide whether distribution category of two population treatment user chi-square is homogeneous. We will also often organize our data. Okay, for example here. So this is mass incorporations. Okay, data on average, the new mixed color is candidate will contain 13% of each of brown, okay, reds, and 14% yellow 16%, green and 20% and 34% blue. So the one way to summarize the data from this one is one way table distribution, which is blue is 9 count, okay, because it said orange is 8 and the rest. So this is, for example, total is 60. So the sample proportional blue is 9. We have 9 divided by the total is 0.15. Okay. So since the company claimed 24% are blue, so we might believe that some fishy is going on. Okay, this is data, suddenly they claim it 24. Actually, your calculation is only 0.15. So we could use the one sample Z test of the hypothesis, which is if H naught P equal to 0.24, H1 P is not 0.24. So whereas P the true populations of the blue, we could then perform a significant test for each of the remaining colors. How to do this one? So your first you should to have the hypothesis. The H naught hypothesis is the company stated the color distributions of milk candidate is correct, 24% just now. Second hypothesis is not correct. Okay, we calculate is 15%, something about that. So how to find it? Okay, we can also write the hypothesis H naught P blue is 24%, 20%, 16%, 14%, 30% and 13%. So at least one PI is incorrect. So you want to check, is it correct or not correct? Correct or not? So the P color true populations of candidates of P. Okay, we compare the observation count and also the expected count. So what we do here, we need to calculate the average number of blue is N times P. Okay, so N times P. So your N is 60, total is 60. Your population of blue is 0.2. So you get 14.4. Okay, this is your expected count of blue. So we calculate others. Orange is 0.2 times the N, P times N. We get 12, 9.6, 8.4 and the rest. Okay, this is your observations. 9, 8, 12, 15, 10 and 6. But your expected calculation from here is 14.4, 12.4, 9, 8.4 and the rest. So from the data, give convincing evidence against the null hypothesis. We compare the observed count from our sample with expected H naught is true. So if the observed count are far from the expected count, that the evidence was seeking. So this is the data observation on the blue color. We see that in other category expected is higher. In other category, yellow for example, the observed is higher. So we see some fairly large difference between the observation and expected. So you can see the large difference here. So how likely the difference this larger occur by chance of random, by 60 by the populations as our questions. To answer this, we need to use the chi-square statistics. So this is the formula, x square. Previously I taught you, x square equal to observation minus expected square divided by expected. So in this case, this is our observation 9, this is our expected. So 9, okay, see, minus 14 square divided by E 14. So plus the second one, 8 minus 12 square divided by 12. Okay, you do it plus everything. At the end you will get 10. You sum it, summation everything, you will get 10.180. So think of x square a measure of the distance of the observation count from the expected large value x square are stronger evidence. Okay, large value of x count note, because they say that observation count are far from what we would like to H note with true. Small x will be consistent in, suggest that data are consistent with the hypothesis. Okay, so how to do it? You need to use the distribution. The chi distribution are family of distribution that can take it positive and negative. This is chi square distribution. Okay, so now our x square, okay, our x square is 10.180. Okay, how to see the table from p value of table? So we need to find 5 row. Why 5 row? Your df is 6 minus 1. Okay, how to get 6 minus 1? So you have 1, 2, 3, 4, 5, 6. So k minus 1, just a k minus 1. 6, that's why you had equal to, okay, equal to 6 minus 1, which is 6 minus 1 equal to 5. That's why you get the 5 here. Okay, so the F row you need to open, okay, you need to open the given chi-square table. Okay, so this is a chi-square tables. So now your df is 5. Okay, back to your data. Your data is 10.18. So find here 10.18. 10.18. 10.18 is in between here. 0 in between this one. Okay, 0.1 and 0.05. Okay, so that's why you get this one. Okay, 0. Okay, this one 0.9.2. 10.1 is something around here. That's why under the table of 0.1, 0.05. Then you need to calculate. Then when you calculate, you notice that your p value is between 0.05 and 0.01. So it's greater than alpha is 0.05. So therefore, we fail to reject the hypothesis. H note, we don't have sufficient evidence to conclude that the company claim color distribution is incorrect. So we are in the range of here. Okay, your p value is in greater than 0.05. So that's why H note failed to be rejected. So the evidence conclude company claim color distribution is incorrect. Okay, so random, the data comes well designed. Random sample from a random 10% when sampling without replacement check, and large all expected is greater than 5. Okay, so before we start the key test, we have two important caution offer. Okay, the chi-square test statistics compare the expected count. Okay, don't try to perform calculation with observation expectation profile in each category. Okay, when large, small samples condition, be sure to examine an expected count, not the observation count. Okay, this is the formula. Okay, if H notes, the stated distribution of category variable is population interest is correct. Okay, the stated of category is not correct. Normally this one is correct, this one is not correct. Then you need to calculate this x square notes. Okay, you need to find the p value. Then you need to find your x square value based on the table. What is k? K is a k minus 1. Then check the table. Then you get the answer. Okay, this is another examples. Okay, you need, okay, first, okay, you need to find the x square test. How to find? Okay, okay, because of sampling without replacement, so it at least n times p is about 800 initial player. So in the season when the data collect, there were 879. Okay, so the expected count is 20, at least 5. So you calculate, this is your y. So your 32 minus your mean. 32 minus, this is O minus E. So what is E is 20. Where you get the 20 is, then the expected count is or 80 divided by 4 equal to 20. Why 4? 1, 2, 3, 4. 1, 2, 3, 4. You have k n divided by 80 times 4. N divided by k, where is your n is 80 divided by k is 4. So you get 20. So this is your E. So O divided by E, total you get 11.2. The summation of everything. So 11.2 in this case, you find the F equal to 3 because of K is 4 minus 1. K is 3. Find the table of 3, the F3. So in this range, so your data will be 11.2. So something around here. So it's higher than 0.01, lesser than 0.05. So because of P is 0.01, less than alpha is 0.05, so we need to reject H notes. So we have convincing evidence the birthday of NHL player are not evenly distributed across the 4 quarters of the year. Okay.